Chapter 3, Section 7 is adding and subtracting rational numbers. That's a fancy way of saying adding and subtracting fractions. But there's a catch. This time there's going to be positives and negatives. We've already done fractions once this quarter, but now we're going to really and truly throw in positive and negative numbers and expect you to know how to work with them. The content objective is students will demonstrate application of the additive inverse and understanding addition and subtraction of rational numbers. Additive inverse, that may be equations, we shall see. And the pacing guide says that this is going to be a single day lesson, so it shouldn't take too long to knock this one down. Let's get started. Of course, you want to start off by writing down 3-7 and, whoops, not launch the lesson. That's not the one we want. Add and subtract rational numbers is what you want, because that's going to be your lesson title. One of the largest temperature variations in a single day was during the winter of 1972 in Loma, Montana. The temperature rose from negative 47.8 degrees Celsius to 9.4 degrees Celsius in a 24-hour time period. When measuring in Fahrenheit, what is the change over 100 degrees? Okay, when measuring in Fahrenheit, the change was over 100 degrees. That was a single day. The temperature changed over 100 degrees. Now, I want to stop and say something here. This negative 47.8 degrees Celsius, that's freaking cold. Freezing at Celsius is 0 degrees. So let's find out just how cold this is. Convert negative 47.8 degrees Celsius to Fahrenheit.
That would be minus 54 degrees Fahrenheit.
Did y'all catch that? Negative 54 degrees Fahrenheit. Fahrenheit freezes at 32 degrees. That's cold. Why would you live someplace that gets that cold? I don't understand. But alas, we need to keep moving here. How do you think you could find the change in temperature? These are some of the things we're going to be learning and working with in this lesson. Two numbers are opposites. Two rational numbers are opposites if they are represented on a number line by points that are the same distance from the opposite sides and 0. That, I'm pretty sure, is going to be one of your vocabulary terms. Opposite is a target term here. 2 points, 3/4 and negative 3/4, are graphed. They are opposites because they are both 3/4 of a unit from 0. They're on opposite sides of 0, and they're the same distance from 0. Definition: opposites. If you were to add these two numbers together, you would find that the sum of the number and its opposite, or also known as the additive inverse, is 0. Negative 3/4 plus 3/4 is equal to 0, and the animation demonstrates how the sum of the additive inverse and its original number is going to equal to 0. So, how do we find an additive inverse? It's really stinking easy, guys. Find the additive inverse of negative 7/8 on a number line. 7/8 is the same distance from 0 as negative 7/8, so 7/8 is the additive inverse. That's all there is to it. Now we're going to take the original value. It's negative 7/8 on the number line here. Our additive inverse is a positive 7/8 on the number line here. Notice how these two numbers are equal distance from 0, but on opposite sides of 0. Additive inverse. I'm not even going to ask you to pause the recording to answer this one. What is the additive inverse of of 0.65? It's going to be negative 0.65. Take the sign, whatever sign's on it, change it to the other sign. It's that simple. Super easy stuff. So let's learn a little bit about using this. Annalise earned $36.82 at her part-time job. She also earned $18.50 sitting on a baby. Why we keep paying people to sit on babies? I don't get it. I don't understand. But find the total amount she earned, the additive inverse, and describe the situation so that Annalise ends the week with $0. So Should Annalise babysitting and part-time job money be represented with a positive or negative number? Well, these are positive numbers because that's money she's brought in. She has earned it, and since she's earned it, it's going to be a positive number. First thing we're going to do is find the total amount earned. We're going to add 3682 and 1850. Let's see here. That's going to give me 46, 54, 82, 55, 32, I believe is what that's going to be if I did that number right in my head, and I did. So the total amount she earned, $55.32. Next, we're going to take and say, what would the additive inverse be? I'm sorry, what number could you add to 5532? In other words, what's the additive inverse of 5532 to get it to equal to 0? That's going to be negative 5532. This stuff really isn't this hard, guys, okay? And moving from there, describe a situation in which Annalise ends the week with $0. Well, she could lose $55.32. She could spend $55.32. She could donate $55.32. All of those represent a loss of the money. While earning it means she would have made more. Finding it, that's a gain. It's a plus sign. And getting it as a gift, that's a gain. It's a plus sign as well. So that answer is going to be correct. Finish the problem. Annalise ends the week with $0. You use this situation to, you can use one of the situations to create your own. So here you go. Annalise had earned $55.32, but she was passing this homeless dude on the street and he looked really hungry and didn't have any boots, so she gave him that $55.32 so he could buy some new boots so he wouldn't have his toesies freeze off in that negative, what was it, negative 42 degree Celsius winter that's coming wherever they're living up in the cold Arctic North. Easy math. You might notice I'm not real clean shaven today. That's because it is Saturday. This is 6:45 p.m. on Saturday night, and look at me. I'm sitting here doing homework. Kind of depressing, isn't it? David spent $6.29 on lunch and $2.54 on a new notebook. Find the total amount he earned, the additive inverse, and describe its situation so that David ends the day with $0. First off, it says find the total amount. I want you to notice they already have a negative sign here. The negative sign's in the front because he spent money, that means it's going out, on both lunch and a new notebook. So whatever number we come up with here, it's going to be negative. So let me do that in my head real quick. That's going to be $2.79, $2.83, I believe, 2.83. And remember, this is a negative because that negative sign's out front. Did I do bad math? Hold on. Yeah, I did do bad math. Why did I say 2? It should be $8. So let me try that again. There we go. Not sure where my 2 came from. So it's a negative $8.83. That was his expenditure for the day. What's the additive inverse going to be? It's going to be a positive $8.83. I mean, how hard can this be, guys? The rules that apply to adding fractions and decimals also apply to rational numbers. The rules for adding integers also apply to positive and negative rational numbers. And we're going to use a chart to see some strategies for how to add rational numbers in different form. First, let's look at terminating decimals in words. If the fractions are decimals that terminate, we can use terminating decimals to add or subtract. So they took a negative 1/5 plus 0.8 is equal to negative 1/5 plus 4/5. So they converted that 0.8 into 4/5. Likewise, over here they had negative 1/5 plus 0.8, and this time they can say that negative 1/5. That's the same thing as negative 0.2. So you could convert them to a common base, whether it's either fractions or decimals, and work them that way. However, for non-terminating decimals, if fractions or decimals that repeat non-zero numbers, then we really need to go to fractions. Because if we're trying to add add repeating patterns, we're never going to get all the numbers in, so we're never going to get a precise answer. Remember in the last lesson I talked to you about how fractions are precise. So in this case, you have to take the number and convert it to the fraction, even though this is not a good example because that's a terminating decimal, but you have to convert the decimal to a fraction, because fractions are always going to give you the exact answer, not just something that's really close to it. When a fraction is negative, the sign may be applied to the fraction, and the numerator, the fraction itself, as you see here with negative 2/3, you can put in the numerator like you see there with negative 2. Whoop, that went too big. And you can put in the denominator like you see here in negative 3. If you were adding two fractions with negative sign, the sign is usually applied to the numerator. So if you're going to be adding or subtracting them, general rule, just stick that sign in the numerator and go with it. It really doesn't make a difference where it goes. And they give us a question, why would it be difficult to add negative 2.5 and positive 3.16 repeating? Because that repeating number, where do you choose to stop it? It's going to give you an imprecise answer. So now we're going to take and add negative 3 5/9 and 1 2/9. You've got signs are different. What I teach you earlier, find the difference. But before we can do any of that, we need to figure out how we want to work them. Do we want to keep them as mixed numbers? Do we want to place them as improper fractions? These are important questions you need to ask yourself before you start the problem. The textbook chose to start off by changing them to improper fractions, and really that's a good idea, because when you have differences here, if you're adding them, it's not so bad trying to leave them as mixed numbers, but when you're subtracting, you're finding differences, it gets real ugly when you have them as mixed numbers. So they converted each of these into an improper fraction. After they did that, then they said, well, the 9 is a common base, which not necessarily exactly the way I'd show my work. And then they said up top, signs are what? Signs are different. Find the difference. With a sign from the larger number going in front of the answer, give them 9/21. And finally, in the end, they're going to take that 9/21, negative 21/9, convert that back into a mixed number, which means they simplified it. That's what they did. They divided by 3/3 here. 3 went into 21 7 times. 3 went into 9 3 times. And negative 7/3, that's equal to negative 2 1/3, which is going to be their final answer. And I'm not going to bother typing that in, because you know what? They gave it to us right here. No reason to type it in. Kind of a waste of time. Our talk about it says, why is it important when adding rational numbers to rewrite them as mixed numbers, to rewrite the mixed numbers as improper fractions? It really prevents a lot of mistakes as far as carrying and borrowing and things of that nature that you would have to do. And we're not going to go too deep into that, but we may talk about it at some point later. Alright folks, now it's going to be your turn. Pause the video and solve this problem, which will hopefully load here in just a second. I'm at home, my internet's dreadfully slow. There it is. Pause the video, work the problem. I look forward to seeing if you can get the right answer. So did you do it? Let's see what I'm going to do. First thing I'm going to do is I'm going to take and make them into improper fractions. 10 times 4 is 40, plus 3 is going to be, whoops, give me my pen back here, 43 over 10. Nope, not is equal to, plus, next thing is going to be a negative. 10 times 1 is 10, plus 9 is 19 over 10. And this is probably a good time for me to point out that I have an ugly problem here. And I've talked about, how do you make an ugly problem pretty? You multiply the sign. So a positive times a negative, that's going to become a negative. So now I'm going to take and make that 43 over 10 minus 19 over 10, because a positive times a negative is a negative. I already have a common denominator. All I have to do, 19 minus 43, that is going to be 24 over 10. That'll simplify down. You can divide by 2 over 2, which is going to make that 12 over 5, which is the same thing as saying 2 and 2/5 for your final answer. The answer is positive. All is good. Now, what if we had tried to work it just for kicks and giggles? Let's see what would have happened if we had tried to work it as a mixed number. So let's take a look here on how this thing would have worked out if we tried to do it this way. Now, what I'm going to do first is I'm going to go ahead right over here and I'm going to make my ugly problem pretty. So I'm going to have 4 and 3 over 10 minus 1 and 9 over 10. Now, the issue is the number we're subtracting in the numerator here, 9, that's bigger than the number we have here, the 3. So I'm going to have to do some borrowing. I'm going to borrow from the 4, making it a 3, plus 1 and 3/10 minus 1 and 9/10. So the 3 plus 1 is 4. Well, that 1 is the same thing as saying 10 over 10. So now I could write that as 3 plus 10 over 10 plus 3 over 10 minus 1 and 9 over 10. You with me? 10 plus 3, that now gives me 10 and 13 over 10 minus 1 and 9 over 10. Now I can say 3 minus 1, that's going to equal to 2. 13 minus 9, that is going to equal to 4 over 10, and that of course simplifies to be the same 2 and 2/5 we found doing the problem right there. Do you see why we want to change them to an improper fraction? Which looks cleaner, this or that? Improper fractions, a better way to go. I think this is going to be a really good spot to end part 1 of this video. Come back and watch part 2 as we dive into doing fractions and decimal numbers together. How are we going to solve these problems?